sequencing allows scientists to analyze RNA levels for various cells. Previously, this has been done with bulk RNA-seq, which finds the average RNA production across cells in a tissue. However, as of 2009, scientists can now do single-cell RNA sequencing. This isolates production in individual cells, so many cells in the same tissue can be analyzed separately. This has great potential in personalized medicine. Initially, one might wonder why it is so important to determine the RNA levels individually by cells. Let's look at an example of when an average is not informative. Let's say my cat, scRNA-seq, has been very sick even though I feed him on average twice a day. This statement could be entirely true while still not being healthy for my cat. Look at this. If I feed my cat 9 times on Monday, twice on Tuesday, not at all Wednesday and Thursday, and then once a day for the rest of the week, he is fed on average twice a day. My cat, however, feels very ill. Instead of a normal curve, which shouldn't be assumed, the distribution looks more like this. Similarly, some tissues have normal RNA production on average, but have some problematic cells that are hurting the organism. For example, a tumor tissue may have mostly cells that will respond to chemo treatment, but a few cells that don't. That means after treatment, only those cells will be alive to reproduce, causing a relapse for the patient. Now, doctors have the potential to predict this relapse and make an appropriate treatment plan. This technology has also been used to determine how the nervous system develops, pinpointing exact neurons that are abnormal, contributing to conditions like Parkinson's and autism. It also allows scientists to determine the epigenetic profiling in just one cell. The process for single-cell RNA sequencing is time-consuming and difficult. The first step is single-cell isolation and capture, so the analysis can be focused on one cell. Next is cell lysis, so the RNA of interest can be accessed through the breakdown of the cellular membrane of the isolated cell. The next step is reverse transcription, turning the primed RNA into cDNA, which is short for copy DNA. This synthetic DNA is amplified, typically through a PCR reaction, and then a library is prepared for analysis. This whole process must be repeated about 500 to 10,000 times to get the full analysis of a tissue. Bioinformatics analysts use the prepared libraries to cluster cells by similarities. Due to the limited sample size, however, there is a large potential for error, especially due to noise. Although this technology can do amazing things, it has many drawbacks. It is expensive, time-intensive, and requires highly specific equipment. Despite these challenges, it has the potential to become the future of bioinformatics and personalized medicine.